a place in the cosmos where gravity reigns supreme, a region so dense and powerful that nothing, not even light, can escape its pull. These are black holes, cosmic enigmas that challenge our understanding of space, time, and reality itself. Invisible yet formidable, black holes are the universe's ultimate paradox, simultaneously void in force, absence, and presence. Today, we embark on a journey into these mysterious giants, venturing where few have dared, exploring the secrets they hold and the extraordinary phenomena surrounding them. Our story begins with a simple question: what is a black hole? At their core, black holes are regions of space where matter has been compressed into an infinitely small point called a singularity. Here, gravity is so intense that the familiar rules of physics break down. Surrounding the singularity is the event horizon, the point of no return. Cross this boundary, and escape becomes impossible. Light itself cannot flee, which is why black holes are invisible, detectable only through their interactions with nearby stars, gas, and dust. The concept of black holes was first predicted by Albert Einstein's theory of general relativity. In 1915, Einstein revolutionized physics by showing that mass and energy warp the fabric of space-time like a heavy ball, distorting a stretched rubber sheet. But it wasn't until the 1960s that physicists like John Wheeler gave the name black hole to these strange, all-consuming regions of space. Since then, black holes have moved from theoretical curiosities to observable phenomena, thanks to advances in telescope technology and astrophysical research. Yet black holes are far from uniform. They come in astonishing varieties. Stellar black holes, formed from the collapse of massive stars, can be tens of times the mass of our sun. Supermassive black holes found at the centers of galaxies can weigh billions of times more than our sun, influencing the motion of entire star systems. And then there are the elusive intermediate black holes, cosmic orphans whose existence hints at processes we are only beginning to understand. But why do black holes fascinate us so deeply? Perhaps it's their defiance of the ordinary. They are cosmic laboratories, testing the extremes of physics, where time slows, space curves, and matter behaves in ways that seem almost magical. They are the ultimate frontier, a place where humanity's understanding of the universe is both humbled and inspired. In the following journey, we will traverse the life cycle of stars, witness the violent birth of black holes, dive into their invisible maelstroms, and peer into the mysteries of supermassive monsters at galactic hearts. We will encounter phenomena so strange, they challenge the limits of imagination. Accretion disks glowing with X-rays, jets of matter shooting across light years, and the mind-bending warping of space-time itself. Welcome to the abyss. Welcome to the hidden architects of the cosmos. This is the story of black holes, as told through the lens of science, discovery, and wonder. And as we venture deeper, remember, the universe is stranger and more beautiful than anything you could ever imagine. The story of black holes begins long before their formation, in the fiery hearts of massive stars. Stars are cosmic furnaces, nuclear reactors where hydrogen fuses into helium, releasing staggering amounts of energy. For millions or even billions of years, a star balances a delicate struggle, gravity pulling inward, pressure from fusion pushing outward. But when a star exhausts its nuclear fuel, this equilibrium shatters. Without fusion to counteract gravity, the star collapses under its own weight. For stars significantly more massive than our sun, this collapse is catastrophic. The core implodes, compressing matter into a region so dense that even atoms are crushed. In an instant, the star's core transforms into a singularity, a black hole. The outer layers may explode outward as a supernova, briefly outshining entire galaxies, while the core disappears into a region from which no light can escape. This violent birth is both an ending and a beginning, a cosmic rebirth that seeds the universe with black holes and the elements forged in stellar furnaces. Not all black holes are created equal. Stellar black holes typically weigh between 5 and 20 times the mass of the Sun. Yet their density is incomprehensible. Imagine squeezing a mass greater than the Sun into a sphere barely 20 kilometers across, roughly the size of a city. The gravitational pull near this object is so intense that time itself slows, a phenomenon known as time dilation, predicted by Einstein's theory of relativity. A minute near a black hole can stretch into hours, days, or even years for a distant observer. Supermassive black holes, however, dwarf even these stellar titans. Lurking at the centers of galaxies, including our own Milky Way, these cosmic leviathans can weigh millions or billions of times more than our Sun. Their origins remain a mystery. Did they form from the collapse of gargantuan stars in the early universe, or through the merging of smaller black holes over cosmic time? Or did they grow by devouring gas, dust, and even stars, feeding an insatiable appetite that continues to this day? Scientists are still piecing together these cosmic puzzles. Black holes are not mere cosmic vacuum cleaners, they are engines of creation as well. Their gravitational influence shapes galaxies, orchestrates the motion of stars, and funnels gas into brilliant accretion disks that shine in X-rays, revealing their presence. Around some, matter is expelled in spectacular relativistic jets, beams of particles traveling near light speed, illuminating the cosmos with their energy. These jets can stretch across hundreds of thousands of light years, a testament to the extraordinary forces black holes unleash. As we trace their formation, one thing becomes clear. Black holes are not anomalies. They are essential players in the cosmic story. They mark the endpoints of stellar life, yet they also shape galaxies and influence the evolution of the universe itself. They are, paradoxically, both destroyers and creators, portals into realms where the known laws of physics are stretched to their limits. In the next chapter, we will step closer to the edge, approaching the event horizon itself, exploring what lies at the boundary of the unknowable. We will encounter phenomena that defy intuition, where light bends, time dilates, and reality itself seems to warp under the gravity of a black hole. To understand a black hole is to approach a boundary unlike any other in the cosmos, the event horizon. This invisible line marks the point of no return. Cross it, and not even light can escape. It is a threshold where the familiar rules of the universe begin to unravel, and where our intuition about space and time fails. The event horizon is not a physical surface you could touch, yet it exerts a gravitational dominance so absolute that it defines the black hole itself. Imagine falling toward a stellar black hole. From afar, observers see your descent slow, your image stretching and reddening as the black hole's gravity bends light around you. Time dilates, seconds, for you may stretch into years for someone watching from a distance. You would see the universe outside accelerate, stars racing past as you approach the horizon. But from your perspective, the journey feels almost instantaneous. A silent plunge into darkness. At the heart of a black hole lies the singularity, a point where density becomes infinite and space-time curvature reaches its peak. Here, gravity is unbounded, and the known laws of physics cease to operate in any conventional sense. General relativity predicts this extreme, yet it also clashes with quantum mechanics, which governs the microscopic world. This conflict is one of the greatest mysteries in modern physics. A singularity is a place where Einstein's universe meets the quantum realm, and our current theories are incomplete. Surrounding the singularity, many black holes are encircled by accretion disks, swirling rings of gas and dust heated to millions of degrees as they spiral inward. These disks glow brilliantly in X-rays, a cosmic beacon signaling the presence of a black hole that would otherwise remain invisible. Matter falling into a black hole is not simply consumed. It undergoes extreme compression, friction, and acceleration, releasing energy that can outshine entire galaxies. Some black holes launch relativistic jets, beams of charged particles propelled outward at near light speed. These jets can extend for thousands, even millions of light years, shaping galaxies and influencing star formation across vast cosmic distances. They are among the most energetic phenomena in the universe, a dramatic reminder that black holes are far from passive objects. Recent discoveries have expanded our understanding further. Gravitational waves, ripples in space-time itself, are emitted when black holes collide, sending shock waves across the cosmos. Detected for the first time in 2015, these waves opened a new window into the invisible universe, allowing scientists to hear black holes as they merge, a symphony of cosmic cataclysm invisible to the eye. As we approach the event horizon, the universe begins to feel unfamiliar, even surreal. Time slows, space stretches, and reality is reshaped by gravity's ultimate authority. Here, at the edge of the unknown, black holes challenge our understanding, inviting us to rethink what we know about matter, energy, and the fabric of existence itself. Just outside a black hole's event horizon, the universe transforms into a scene of raw, unimaginable energy. Here, in the accretion disk, a swirling maelstrom of gas, dust, and stellar debris, matter races at incredible speeds, spiraling toward oblivion. Friction within the disk heats this matter to millions of degrees, causing it to glow in X-rays and gamma rays. To distant observers, these emissions shine like cosmic lighthouses, revealing the presence of an object that, by definition, cannot be seen. Accretion disks are not uniform or calm. Turbulence reigns supreme. Magnetic fields twist and coil, channeling material into spiraling currents and sometimes ejecting it as relativistic jets, narrow beams of plasma propelled at nearly the speed of light. These jets can stretch across thousands, even millions of light years, reshaping entire galaxies in their path. They are reminders that black holes are not just cosmic drains. They are engines of creation and destruction, sculpting the universe on an unimaginable scale. The intense gravity near a black hole also warps space-time itself, bending light in ways that defy everyday intuition. This phenomenon, called gravitational lensing, can magnify and distort the images of stars and galaxies behind the black hole, creating rings, arcs, and eerie duplications. Astronomers use this effect to study distant parts of the universe, turning black holes into natural cosmic telescopes. One of the most extraordinary revelations of recent decades is the existence of supermassive black holes at the centers of galaxies. These giants, weighing millions or billions of times the mass of the Sun, dominate the motion of stars around them. In some cases, they ignite as quasars, blazingly luminous cores that can outshine entire galaxies. Quasars are powered by matter falling into the supermassive black hole, releasing energy at rates that challenge human imagination. Observing them, we witness gravity's power transformed into light, a cosmic paradox of destruction and illumination. Even smaller stellar black holes exert profound influence over their surroundings. When paired with a companion star, they siphon gas from the stellar neighbor, forming an accretion disk that flares with X-ray radiation. These X-ray binaries serve as laboratories for studying the extremes of physics, offering insight into gravity, magnetic fields, and the behavior of matter under conditions impossible to recreate on Earth. And yet, despite their power, black holes remain invisible to direct observation. It is only through their gravitational effects, the glowing disks, and the violent jets that we perceive them. In 2019, the Event Horizon Telescope achieved a historic breakthrough, capturing the first ever image of a black hole's shadow in the galaxy M87. For the first time, humanity glimpsed the silhouette of a singularity against the glowing halo of its accretion disk, a profound confirmation of theories that had been decades in the making. The edge of a black hole is a place where light fights to escape, where matter reaches the brink of annihilation, and where the very fabric of reality twists under the weight of gravity. It is a region both terrifying and beautiful, a testament to the extraordinary forces shaping the cosmos. A clock ticking normally on Earth. Now picture that same clock hovering near the edge of a black hole's event horizon. To an outside observer, the hands of this clock appear to slow, crawling forward at a pace that stretches into eternity. This is time dilation, a phenomenon predicted by Einstein's theory of general relativity, where gravity can stretch and bend time itself. Near a black hole, time is no longer universal. It becomes relative, a fluid dimension warped by the immense pull of gravity. The closer you get to a black hole, the more extreme the effects. For a stellar black hole, minutes for someone falling toward it could correspond to years passing for someone watching from a safe distance. Around a supermassive black hole, time slows even more dramatically. In a sense, black holes are cosmic time machines, warping reality in ways that defy everyday intuition and challenging the very notion of what now means. Time dilation is not just theoretical. It has observable consequences. Astronomers studying X-ray binaries and stars orbiting supermassive black holes witness these effects firsthand. The stars near the Milky Way's central black hole, Sagittarius A star, move at incredible speeds, and their light experiences gravitational redshift, stretching to longer wavelengths as gravity stretches both space and time. These observations confirm that black holes are laboratories for testing the limits of physics, where Einstein's predictions meet reality. But the warping doesn't stop at time, it extends to space itself. Near a black hole, space stretches and curves. The gravitational pull is so intense that it bends light around the black hole, creating distorted and sometimes multiple images of background stars. If you were to hover near the event horizon, the universe would appear bizarrely warped. The sky compressed above, stars smeared into arcs, and light itself twisted into spiraling patterns. This cosmic funhouse is a visual testament to the extraordinary forces at play. Inside this distorted space-time, the very notions of cause and effect are challenged. Paths that seem straight from afar curve unpredictably. Particles orbit at near-light speeds, colliding and releasing vast bursts of energy. Matter that falls in is stretched and torn by tidal forces, a process known as spaghettification, an extreme stretching of objects due to the black hole's gravity, Even atoms can be elongated and ripped apart as they spiral toward the singularity. Time dilation near black holes also sparks profound philosophical questions. If you could survive the journey, could you witness the future of the universe in a fleeting instant? Could you return to your origin to find centuries or millennia have passed? While the practicalities make such journeys impossible, these questions illuminate the profound ways black holes challenge our understanding of time, life, and existence. As we explore further, we will encounter black holes not as isolated anomalies, but as central architects of galaxies, shaping the motion of stars, influencing star formation, and even acting as cosmic engines capable of sculpting entire regions of space. The interplay of gravity, matter, and light reveals a universe that is far stranger and more beautiful than we ever imagined. Next, we will follow matter spiraling into black holes, tracing the journey from distant star systems to the glowing accretion disks, and witness how energy is unleashed in ways that dwarf even the most powerful explosions in the universe. As we peer deeper into the heart of a black hole, we encounter a mesmerizing, violent ballet, the spiral of matter toward the event horizon. Stars, gas, and dust caught in the black hole's gravitational grip swirl into a glowing accretion disk, moving at astonishing speeds, sometimes a significant fraction of the speed of light. Within this maelstrom, matter is stretched, compressed, and accelerated, producing intense heat and radiation that can outshine entire galaxies. Accretion disks are nature's most extreme energy engines. Friction and magnetic turbulence within the disk convert gravitational potential energy into heat, light, and high-energy radiation. X-rays, gamma rays, and sometimes even relativistic jets are unleashed, signaling the presence of the otherwise invisible black hole. These emissions allow astronomers to detect black holes across the universe, from nearby stellar remnants to supermassive behemoths billions of light-years away. The journey of matter is not smooth. Tidal forces stretch and twist objects as they spiral inward. This process, called spaghettification, elongates stars and gas clouds into thin, fragile strands before they are finally consumed. For larger black holes, such as the supermassive giants at the centers of galaxies, spaghettification occurs more gradually, but the destruction is inevitable. Nothing crossing the event horizon can return. The singularity claims all. Magnetic fields play a crucial role in shaping this cosmic dance. Twisting and coiling around the accretion disk, they generate powerful jets that shoot matter outward at nearly the speed of light. These relativistic jets can extend for thousands, even millions, of light years, carrying energy and material far beyond the black hole itself. In some cases, these jets can trigger star formation in distant clouds, turning black holes into creators as well as destroyers. In the environment near a black hole, conventional physics is pushed to its limits. Matter behaves in ways that seem almost surreal. Electrons and protons collide, radiate, and accelerate, while the curvature of space-time bends the paths of light and particles. Observing these extreme conditions allows scientists to test the predictions of general relativity and understand the behavior of matter under forces impossible to recreate on Earth. Supermassive black holes, in particular, dominate the dynamics of entire galaxies. Their gravitational influence directs the orbits of stars, controls the flow of interstellar gas, and can even regulate the growth of the galaxy itself. Through their accretion disks and jets, these cosmic giants release enormous energy, influencing regions spanning thousands of light years. Yet, despite their immense power, black holes are not just cosmic destroyers. The energy released during accretion contributes to the chemical enrichment of the universe, dispersing elements forged in stellar interiors into the interstellar medium. Iron, oxygen, and carbon, essential building blocks of life, are recycled across galaxies, a reminder that even in destruction, black holes play a role in cosmic creation. Next, we will explore one of the most mind-bending predictions of modern physics: Hawking radiation. The idea that black holes, despite their reputation as eternal traps, may slowly leak energy and even evaporate over unimaginable spans of time. For decades, black holes were thought to be the ultimate prisons of the universe, regions where nothing could escape, not even light. But in 1974, physicist Stephen Hawking made a groundbreaking prediction. Black holes are not entirely black. Instead, they emit a faint radiation, now called Hawking radiation, a quantum whisper from the edge of the abyss. Hawking radiation arises from the strange interplay of quantum mechanics and gravity near the event horizon. In the vacuum of space, pairs of virtual particles constantly flicker in and out of existence. Normally, they annihilate each other almost instantly, but near the event horizon, one particle can be captured by the black hole while its partner escapes into space, appearing as radiation. In this way, black holes slowly lose mass over time, releasing energy in a process that defies their reputation as eternal traps. The implications are profound. Over unimaginably long timescales, even supermassive black holes could evaporate, leaving behind only the faintest imprint on the cosmos. This challenges the very notion of permanence in the universe, suggesting that even the most massive, seemingly unassailable objects are subject to change. Black holes are not absolute endings. They are dynamic, evolving, and in a sense, alive with quantum activity. Hawking's discovery also bridges two seemingly incompatible realms of physics: general relativity and quantum mechanics. General relativity governs the immense gravity of black holes, predicting singularities and event horizons, while quantum mechanics describes the microscopic world of particles and fields. Hawking radiation is a rare phenomenon where these two realms intersect, hinting at a deeper theory that may one day unify the laws of the cosmos. Observing Hawking radiation directly is beyond current technology. The effect is incredibly faint, especially for large black holes, but its theoretical existence has transformed how scientists think about black holes. No longer are they merely cosmic vacuum cleaners or destructive forces. They are active participants in the universe's energy balance, slowly emitting particles and interacting with the surrounding cosmos. In a poetic sense, Hawking radiation reveals that black holes speak, even if in whispers. They communicate the underlying rules of reality, hinting at the hidden connections between gravity, quantum fields, and the nature of space and time itself. Every black hole, from a stellar remnant to a supermassive colossus, is part of a vast cosmic dialogue, a story told in the language of particles, waves, and light. As we continue, we will journey to the centers of galaxies, where supermassive black holes dominate entire star systems, exploring how these titans influence galactic evolution and drive some of the universe's most spectacular phenomena. At the heart of nearly every galaxy lurks a cosmic giant, a supermassive black hole. These titans can weigh millions or even billions of times more than our sun, exerting gravitational influence over entire star systems. While invisible themselves, their presence shapes the motion of stars, directs the flow of interstellar gas and orchestrates the dynamics of galaxies on scales that defy human comprehension. Some supermassive black holes awaken in spectacular fashion. When vast clouds of gas and dust fall toward them, they ignite as quasars, the universe's most luminous beacons. A single quasar can outshine its entire host galaxy, emitting energy equivalent to trillions of suns. These luminous cores were particularly common in the early universe, signaling the rapid growth of black holes and their role in shaping cosmic evolution. Quasars are powered by accretion disks spiraling into the black hole, where friction and gravitational forces heat matter to extraordinary temperatures. Magnetic fields twist and channel material into relativistic jets that shoot across thousands of light years, sometimes piercing the galaxy itself. These jets can trigger star formation in some regions, while clearing gas and dust from others, demonstrating the dual nature of black holes as both creators and destroyers. Our own galaxy, the Milky Way, harbors a supermassive black hole named Sagittarius A star, weighing around 4 million times the mass of the Sun. While currently relatively quiet, its influence is undeniable. Stars orbit it at incredible speeds, their paths bent by gravity, and occasional flares of X-rays and infrared light reveal that even a dormant, supermassive black hole can interact with its surroundings in dramatic ways. The existence of supermassive black holes raises profound questions. How did they form so quickly after the Big Bang? Did they emerge from the collapse of gargantuan primordial stars, or grow steadily by devouring surrounding matter? Observations of distant quasars suggest that some formed when the universe was only a fraction of its current age, hinting at processes that are still mysterious to astrophysicists. Beyond their immediate environment, these cosmic giants influence galaxy evolution on enormous scales. By regulating star formation, redistributing matter, and shaping galactic structures, supermassive black holes are central architects of the universe. They demonstrate that gravity, in its most extreme form, can be both a destructive force and a creative one, sculpting the cosmos over billions of years. The universe is a place of motion, chaos, and unimaginable energy. Among its most dramatic events are collisions between black holes, where two cosmic titans spiral toward each other in a deadly dance, ultimately merging into a single, even more massive black hole. These collisions are not just spectacular, they are cosmic symphonies, sending ripples through the very fabric of space-time known as gravitational waves. Gravitational waves were first predicted by Albert Einstein over a century ago, as part of his general theory of relativity. These waves are distortions in space-time, traveling outward at the speed of light, carrying energy from massive accelerating objects. For decades, they remained theoretical until the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the first signal in 2015, a collision of two stellar black holes over 1 billion light-years away. Humanity had finally heard a black hole. The energy released in a black hole merger is staggering. In a fraction of a second, these collisions can emit more energy in gravitational waves than all the stars in the observable universe emit in light over the same period. This energy does not blast matter outward. It disturbs space-time itself, stretching and squeezing distances in a way that is imperceptible without incredibly sensitive instruments. Yet, by detecting these minute distortions, scientists can trace the history of black hole interactions across the cosmos. The merging process is a complex ballet. As two black holes orbit each other, they accelerate, their gravitational fields intertwining, The closer they get, the faster they spiral, radiating gravitational waves that carry away energy. Finally, in a violent crescendo, they collide, forming a new black hole that vibrates like a ringing bell, emitting a final burst of gravitational waves as it settles into a stable state. These signals reveal the masses, spins, and dynamics of the colliding black holes, offering an unprecedented glimpse into phenomena invisible to traditional telescopes. Black hole collisions are not limited to stellar remnants. Supermassive black holes at the centers of merging galaxies can also collide, releasing gravitational waves on scales far beyond human imagination. Detecting these waves remains a challenge, but future observatories may allow us to hear the echoes of galactic mergers, offering a unique way to map the evolution of the universe itself. These cosmic collisions also reshape our understanding of space and time. They confirm that space-time is not an immutable backdrop, but a dynamic, flexible medium, capable of rippling and resonating in response to extreme events. By listening to these ripples, scientists can probe regions where gravity is strongest, matter is densest, and the laws of physics are pushed to their limits. As we continue, we will delve into one of the most enigmatic questions in modern astrophysics. What happens inside a black hole? Beyond the event horizon lies the singularity, a region where density becomes infinite and our understanding of physics begins to falter. It is a place where theory reaches its limits and imagination must take over. Beyond the event horizon, reality itself seems to unravel. This is the domain of the singularity, the very heart of a black hole, where gravity crushes matter to infinite density and the known laws of physics break down. Time and space, which we take for granted, lose all meaning here. The singularity is not just a point, it is a cosmic paradox, a place where our understanding of the universe reaches its ultimate limit. According to Einstein's theory of general relativity, the singularity is infinitely small, infinitely dense, and infinitely curved. All the mass of the black hole is concentrated here, and the gravitational pull is so intense that no force can counteract it. But this is precisely where general relativity clashes with quantum mechanics, the theory governing the subatomic world. One predicts a singularity, the other forbids infinities. The result is a profound puzzle. What really happens inside a black hole? The concept of spaghettification illustrates the singularity's power. As matter approaches the center, tidal forces stretch it along the direction of gravity, elongating and thinning it into nearly invisible strands. A human or star would be torn apart, atom by atom, long before reaching the singularity. Even light cannot escape this fate. Yet what happens at the singularity itself remains one of the most profound mysteries in physics. Some theories suggest that the singularity might not be a true point, but rather a bridge to another dimension, or even a passage to a different universe. Wormholes, speculative tunnels through space-time, remain hypothetical but tantalizing possibilities. Could black holes be cosmic gateways? Could information swallowed by a black hole somehow survive or escape? These questions push the boundaries of science, straddling the line between physics and philosophy. Stephen Hawking's insights hint at surprising resolutions. Through Hawking radiation, black holes may release information gradually, suggesting that even within the singularity, the universe preserves a record of what has fallen in. This leads to the black hole information paradox, a puzzle that has captivated physicists for decades. If black holes destroy information, it violates fundamental rules of quantum mechanics. If they preserve it, then reality may be far stranger than we can imagine. While we cannot observe the singularity directly, its influence radiates outward. Black holes warp space, bend light, and shape the cosmos, offering indirect evidence of the extreme physics at play. In this sense, the singularity is not merely a theoretical concept. It is the invisible hand guiding galaxies, stars, and cosmic evolution. As we journey onward, we will step back from the incomprehensible depths of the singularity to explore how black holes shape galaxies, influence star formation, and even seed the growth of new cosmic structures. The story of black holes is one of destruction, yes, but also of creation, balance, and the hidden architecture of the universe itself. Black holes are more than isolated enigmas. They are central players in the grand architecture of the universe. From stellar remnants to supermassive giants, their gravitational influence sculpts the motion of stars, channels the flow of gas, and orchestrates the evolution of entire galaxies. Far from being mere consumers of matter, black holes are cosmic engineers, silently shaping the universe on scales that dwarf human comprehension. At the heart of most galaxies lies a supermassive black hole, its gravity dictating the orbits of stars in the galactic core. These central titans control not only motion but also the life cycle of matter. Gas clouds spiraling inward feed the black hole, releasing tremendous energy in the process. This energy can ignite surrounding regions, triggering star formation, or paradoxically, blow away gas and suppress new stars. In this way, black holes act as regulators, balancing the growth of galaxies across billions of years. Observations of distant galaxies reveal even more astonishing influence. Relativistic jets launched by accretion disks around supermassive black holes pierce galactic environments with streams of charged particles. These jets travel across hundreds of thousands of light years, interacting with interstellar gas, heating it, and sometimes compressing it into dense knots that spark new generations of stars. In effect, black holes are both destroyers and creators, their energy sculpting matter across cosmic distances. On the largest scales, black holes contribute to the cosmic web, the vast network of galaxies and clusters that forms the backbone of the universe. Their gravitational pull helps anchor matter, guiding the motion of galaxies within clusters and influencing the distribution of dark matter. Without black holes, the universe might look entirely different, lacking the organized structure we observe today. Even stellar black holes play a subtle but crucial role. X-ray binaries and smaller black holes enrich their surroundings with heavy elements, products of stars torn apart by gravity. These elements, iron, oxygen, carbon, seed new star systems and planetary systems, forming the building blocks of planets and life itself. In this sense, black holes are both endpoints and origins, cycling matter and energy in a cosmic feedback loop that spans billions of years. Black holes are also timekeepers of the universe. Their influence affects the formation and evolution of galaxies, determining the pace at which stars are born and die. By studying them, astronomers can trace the history of galaxies, reconstructing cosmic evolution from the early universe to the present day. The story of black holes is thus not one of simple destruction. They are creators, architects, and regulators of the cosmos, invisible yet indispensable. Their gravitational dance shapes everything from the tiniest star clusters to the vast cosmic web stretching across the universe. In the vast expanse of the cosmos, some black holes defy comprehension. These are the extreme titans, monsters of mass and energy that push the limits of physics and imagination. Among them are supermassive black holes, weighing billions of times the mass of our sun, spinning at near light speeds and releasing energy that illuminates the universe across millions of light years. The most massive black holes challenge our understanding of cosmic growth. Some, like TON 618, are estimated to be over 66 billion times the mass of the Sun, dwarfing even entire galaxies. How such titans formed in the relatively young universe is one of astrophysics' greatest mysteries. Did they grow by consuming stars and gas relentlessly? Did they form from the collapse of enormous primordial objects? The answers remain elusive, but their existence reshapes our understanding of what is possible in the cosmos. Spin adds another layer of extremity. Black holes can rotate, dragging space-time itself around them in a phenomenon called frame dragging. The fastest spinning black holes approach the speed of light at their event horizons, twisting magnetic fields, accelerating matter in accretion disks, and launching relativistic jets with unimaginable energy. These spinning titans are cosmic dynamos, converting rotational energy into radiant light and particle jets that can illuminate the universe. Even stellar black holes can display extraordinary properties. Some remnants of massive stars are only a few dozen times the mass of the Sun, yet their gravitational pull can warp light, distort space, and accelerate matter to near-light speeds. X-ray emissions from these systems allow astronomers to probe conditions far beyond anything achievable on Earth, providing laboratories for the physics of extreme gravity. Black holes also interact in ways that produce cosmic spectacles. Colliding black holes merge into even more massive entities, releasing gravitational waves that ripple across space-time. Observations of these events reveal insights into mass, spin, and even the population of black holes across the universe. Each collision is a dramatic testament to the energy and scale of these cosmic giants, events that would dwarf even the most powerful explosions we can imagine. Despite their ferocity, these extremes also provide clues about the universe's formation and evolution. By studying the largest, fastest, and most energetic black holes, scientists can reconstruct the history of galaxies, test the limits of general relativity, and explore the interplay between matter, energy, and gravity in the universe's most extreme environments. As we continue, we will shift our gaze to the invisible. Dark matter, dark energy, and the mysterious role of black holes in shaping the unseen cosmos reveal a universe far stranger than we can observe directly. These invisible forces, intertwined with black holes, guide the dance of galaxies and the evolution of the cosmos itself. While black holes themselves are invisible, they exist within a universe full of unseen forces. Dark matter and dark energy dominate the cosmos, shaping its structure and destiny. Black holes, massive and mysterious, interact with these hidden elements, influencing the cosmic web in ways we are only beginning to understand. Dark matter, an invisible substance making up roughly 27% of the universe, exerts gravity without emitting light. It forms the scaffolding upon which galaxies grow. Supermassive black holes residing at the centers of the galaxies interact with this dark matter halo, affecting star formation, gas dynamics, and the evolution of entire galactic systems. The invisible mass guides the motions of stars, while black holes anchor them in gravitational harmony. Even more enigmatic is dark energy, a mysterious force accelerating the expansion of the universe. While its connection to black holes is less direct, The growth and distribution of black holes over cosmic time provide clues about the interplay of energy, gravity, and cosmic evolution. By studying black holes and their environments, scientists hope to uncover hidden relationships between visible and invisible components of the universe. Black holes themselves may also serve as laboratories for extreme physics. Observing their interactions with dark matter could reveal whether exotic particles, like weakly interacting massive particles, are drawn into their gravitational grip. Could black holes act as cosmic detectors for phenomena invisible to conventional instruments? The possibilities are tantalizing. Gravitational lensing, another cosmic trick, offers insight into this hidden universe. As black holes bend light, they reveal not only their own presence, but also distortions in the surrounding dark matter. By mapping these distortions, astronomers can chart the invisible scaffolding of galaxies, revealing structures that would otherwise remain concealed. The universe, in this sense, is a layered mystery. Black holes are visible only through their effects, yet their influence extends into the unseen realms of dark matter and dark energy. They are both actors and witnesses in a universe shaped by forces beyond human perception. Their gravity sculpts, their presence illuminates, and their mysteries push the boundaries of what we can comprehend. For centuries, black holes were purely theoretical, invisible objects inferred only through their effects on surrounding matter. But in April 2019, humanity achieved the impossible. We saw a black hole for the first time using the Event Horizon Telescope, EHT, an international network of radio observatories spanning the globe. Scientists captured the shadow of a supermassive black hole in the galaxy M87, 55 million light-years away. The image was startling and beautiful. At the center, a dark silhouette. The black hole's shadow was surrounded by a glowing ring of light emitted by the searing gas in the accretion disk. This was not just a photograph. It was proof that Einstein's theories could describe one of the most extreme objects in the universe. The shadow confirmed predictions about the size and shape of the event horizon, and the luminous ring revealed the immense energy released by matter spiraling into the abyss. The achievement required unprecedented coordination. The EHT links telescopes across continents, from the peaks of Hawaii to the deserts of Arizona, from Antarctica's icy expanses to Chile's Atacama Desert, effectively creating a planet-sized telescope. By combining signals using a technique called very long baseline interferometry, scientists achieved the resolution necessary to observe details smaller than the width of our solar system from millions of light-years away. The success of the EHT was a triumph of collaboration, technology, and patience. Data from thousands of hours of observation were combined and processed using supercomputers, revealing a crisp, detailed image that confirmed decades of theoretical predictions. For the first time, humanity glimpsed the edge of a singularity, witnessing the boundary between known physics and the unknown. This historic image also sparked the imagination of the public, transforming black holes from abstract equations into tangible cosmic objects. It allowed us to confront the ultimate paradox, something we cannot see directly, yet whose presence shapes galaxies and influences cosmic evolution, now had a face, or at least a shadow. Beyond M87, the EHT has also imaged the black hole at the center of our own Milky Way, Sagittarius, a star. While smaller and more variable, this observation brings us closer than ever to understanding the hidden giant that governs the stars at the core of our galaxy. The Event Horizon Telescope has shown that even the invisible can be observed. and the unknowable can be glimpsed. Black holes, once confined to theory and speculation, now exist in our minds and our images, a testament to human ingenuity and curiosity. Black holes are not just cosmic monsters, they are gateways to questions that stretch the limits of imagination. What lies beyond the event horizon? Could black holes be tunnels to other regions of space, or even to alternate universes? These ideas, while speculative, emerge from the mind-bending predictions of general relativity and quantum physics, where space-time itself can bend, twist, and connect in ways that defy our everyday understanding. One of the most tantalizing concepts is the wormhole, a theoretical tunnel through space-time that could connect distant points in the universe. While no evidence exists that such passages actually exist, the mathematics of Einstein's equations allow for the possibility. A wormhole could, in theory, provide shortcuts across light years, compressing vast distances into a fleeting journey. Black holes, with their intense gravity and space-time warping properties, are often imagined as the entrances or exits of such cosmic pathways. Time travel is another concept that arises near black holes. The extreme time dilation near an event horizon means that seconds for someone falling into a black hole could correspond to years, or even centuries, passing outside. While surviving such a journey is impossible due to tidal forces, the physics raises fascinating questions. Could black holes allow glimpses into the future, or provide insight into the universe's distant past? They are, in a sense, natural laboratories for studying the nature of time itself. Yet black holes also present paradoxes that challenge the foundations of physics. The information paradox, proposed by Stephen Hawking, questions whether information that falls into a black hole is lost forever, violating quantum mechanics, or somehow preserved. Resolving this puzzle may require a new theory uniting gravity and quantum physics, a theory of quantum gravity that could reshape our understanding of reality. Black holes force us to confront the limits of human knowledge. They are places where intuition fails, where the familiar rules of cause and effect bend, and where the universe tests the very nature of existence. Philosophers and scientists alike are drawn to them not just for their power, but for what they reveal about the cosmos and our place within it. Despite the danger, the mystery, and the unknown, black holes inspire curiosity and wonder. They are natural paradoxes, destructive yet creative, invisible yet influential, eternal yet slowly evaporating. They are both the end and the beginning, the ultimate test of human imagination and scientific inquiry. Black holes are more than the universe's ultimate destroyers. They are its sculptors. By controlling the flow of gas, dust, and stars, they regulate the growth of galaxies and shape the very structure of the cosmos. Supermassive black holes, in particular, act as cosmic engines, influencing everything from star formation to the dynamics of entire galactic clusters. When matter falls into a supermassive black hole, it releases enormous energy through the accretion disk, often triggering powerful outflows and relativistic jets. These jets can heat surrounding gas, preventing it from collapsing into new stars. In some cases, they compress gas in distant regions, sparking bursts of star formation. In this paradoxical way, black holes both suppress and promote the birth of stars, balancing the growth and evolution of galaxies over billions of years. Observations of the early universe reveal that supermassive black holes appeared surprisingly quickly after the Big Bang, Their influence on nascent galaxies suggests that black holes may have been central to the formation of cosmic structure. Without these gravitational titans, galaxies might never have achieved the shapes and sizes we observe today. Their presence provides the gravitational glue that anchors stars and gas, orchestrating the dance of matter on a grand scale. Even stellar black holes contribute to cosmic evolution. As remnants of massive stars, they recycle matter enriched with heavy elements back into the galaxy. When they interact with companion stars or merge, they generate X-rays and gravitational waves, redistributing energy and information across vast distances. These processes ensure that black holes are not merely endpoints. They are active participants in the life cycle of matter. The interplay between black holes and galaxies also informs our understanding of cosmic history. By studying the mass, spin, and distribution of black holes, astronomers can reconstruct how galaxies evolved over billions of years. Black holes are, in essence, archivists of the universe, preserving the story of cosmic formation through their gravitational influence and energetic feedback. Ultimately, black holes demonstrate that destruction and creation are intertwined. Their gravity tears matter apart while shaping new stars and galaxies. Their jets and radiation sculpt interstellar gas while regulating the growth of cosmic structures. In the universe, endings are inseparable from beginnings, and black holes are the ultimate proof of this cosmic cycle. Black holes captivate not only scientists but also the human imagination. Their mystery, power, and paradoxical nature have inspired generations of artists, writers, and filmmakers to explore the unknown. From early science fiction novels to blockbuster movies, black holes serve as symbols of both fear and wonder, cosmic doors to realms beyond comprehension. In literature, black holes often represent the ultimate unknown. Writers use them as metaphors for infinity, mortality, and the limits of knowledge. Their invisibility and destructive power evoke awe, while their connection to time dilation and relativity sparks philosophical questions about reality and perception. They are not just objects of science, they are mirrors reflecting humanity's curiosity and existential wonder. Cinema has amplified the allure of black holes. Films like Interstellar have dramatized the physics of these objects, showing the intense gravitational pull, spaghettification, and time dilation near the event horizon. Collaborating with physicists, filmmakers have rendered scientifically accurate visualizations, allowing audiences to experience the surreal and terrifying beauty of black holes. These depictions transform abstract equations into vivid, immersive storytelling, bridging science and art. Even in music, art, and popular culture, black holes serve as symbols of the unknown. They represent endings that are also beginnings, destruction intertwined with creation. Their mystery speaks to our innate desire to explore, to understand, and to confront forces far beyond our control. Through imagination, black holes become more than cosmic phenomena. They become tools for exploring human curiosity, fear, and ambition. Science itself is inspired by imagination. Hypotheses about wormholes, time travel, and alternate universes often emerge at the intersection of theoretical physics and creative thinking. Black holes challenge scientists to think beyond conventional limits, to explore ideas that blur the line between reality and speculation. In this way, imagination and inquiry feed each other, expanding both our cultural and scientific horizons. Ultimately, black holes remind us that the universe is far stranger than we can observe directly. They challenge our understanding of space, time, and matter, while igniting a fascination that transcends disciplines. Whether through equations, telescopes, novels, or films, black holes continue to inspire humanity to look upward, to ponder the infinite, and to embrace the unknown. Black holes remain among the most mysterious and compelling objects in the cosmos, and the quest to understand them is far from over. The future of black hole research promises to push the boundaries of technology, theory, and human curiosity, revealing secrets hidden in the darkest corners of the universe. Gravitational wave observatories like LIGO and Virgo have already transformed astrophysics, allowing us to hear black holes as they collide. Future detectors, including the planned space-based observatory LISA, will extend this capability, detecting gravitational waves from supermassive black hole mergers across the cosmos. By listening to these cosmic vibrations, scientists can map the life cycle of black holes and observe phenomena invisible to conventional telescopes. Meanwhile, the Event Horizon Telescope continues to evolve. With higher resolution, additional observatories, and advanced imaging techniques, the EHT will capture even more detailed images of black hole shadows. Scientists hope to study the dynamics of accretion disks, the formation of relativistic jets, and the behavior of matter near the event horizon in unprecedented detail. Each observation brings us closer to understanding the physics of extreme gravity. Theoretical research is also advancing. Quantum gravity, string theory, and other cutting-edge frameworks aim to reconcile general relativity with quantum mechanics, offering potential insights into the singularity and the fate of matter and information inside black holes. These efforts may eventually reveal a deeper understanding of space-time, energy, and the fundamental laws governing the universe. Black holes also provide a laboratory for extreme physics. By studying high-energy emissions, relativistic jets, and interactions with surrounding matter, astronomers can test the limits of physical laws, explore the behavior of matter under unimaginable forces, and probe phenomena that cannot be replicated on Earth. Each discovery informs not only our understanding of black holes, but also the underlying principles of the cosmos itself. As our tools improve and our knowledge expands, black holes are no longer purely objects of theory. They are windows into the fundamental workings of the universe. They challenge us to innovate, to explore, and to question. The future promises discoveries that may redefine our understanding of space, time, and existence itself. Black holes are more than cosmic phenomena. They are profound teachers challenging our understanding of reality and our place in the universe. Their extremes of gravity, time, and energy push the limits of human comprehension, revealing truths that are as philosophical as they are scientific. One of the most striking lessons of black holes is the relativity of time. Near the event horizon, seconds stretch into years, reminding us that time is not absolute. The universe is not uniform or predictable. It is dynamic and flexible, governed by forces that can distort the very flow of reality. Black holes force us to confront the fluidity of existence and the fragility of perception. Black holes also embody the paradox of creation and destruction. They consume stars, planets, and gas, yet their influence drives the formation of new stars, regulates galaxies, and seeds the cosmos with elements essential for life. In the universe, endings are inseparable from beginnings, and even in destruction lies the potential for creation. They are a reminder that the cosmos operates on cycles far larger than human timescales, where life and death are intertwined in a cosmic rhythm. Philosophically, black holes challenge our ideas of knowledge and limits. The singularity represents a boundary to our understanding, a place where known physics collapses and imagination must take over. They confront us with mystery, revealing that not all questions have immediate answers, and that some truths lie beyond observation, awaiting new theories, new tools, or new ways of thinking. On an existential level, black holes offer perspective. The vastness and power of these objects dwarf human concerns, highlighting our smallness in the cosmic scale. Yet by observing, studying, and understanding them, we assert our curiosity and intelligence, demonstrating that even in the face of the infinite, humanity can grasp fragments of truth. Black holes teach humility, wonder, and the enduring pursuit of knowledge. As we leave the edge of the event horizon behind, we carry with us the story of black holes, a story of power, mystery, and cosmic elegance. These dark giants, invisible yet profoundly influential, shape galaxies, bend time, and challenge our understanding of reality. They are both destroyers and creators, paradoxes that teach us about the universe and ourselves. Black holes remind us that the cosmos is vast beyond comprehension. They stretch space, warp time, and harbor energies that dwarf all else, yet they also illuminate fundamental truths. Through their gravity, we see the architecture of galaxies. Through their radiation, we witness energy unleashed on scales unimaginable. Through their shadows, captured by human ingenuity, we glimpse the unseen and confront the limits of perception. Every black hole is a testament to the extraordinary forces that govern the universe. They embody extremes, mass, spin, energy, and gravity that stretch the imagination. They are cosmic laboratories where physics is tested at the edge of possibility, where general relativity and quantum mechanics converge in subtle and dramatic ways. They are reminders that the universe is stranger, deeper, and more beautiful than our daily experience suggests. And yet, for all their power, black holes inspire wonder, not just fear. They are symbols of exploration, curiosity, and the human drive to understand the unknown. Through observation, calculation, and imagination, we bring light to the darkness, turning invisible giants into objects of study, contemplation, and awe. As we close this journey, we are left with both knowledge and mystery. Black holes teach us humility in the face of cosmic scale, patience in the pursuit of discovery, and wonder at the beauty and complexity of the universe. They are reminders that even in the darkest corners of space, there is meaning, structure, and a story waiting to be understood. The universe is alive with energy, motion, and potential. And at its heart, in shadows unseen yet profoundly felt, black holes continue to shape the cosmos, silent architects of creation, guardians of mystery, and eternal symbols of the extraordinary. As we gaze upward, we are invited to dream, to explore, and to continue asking the questions that drive humanity forward. What lies beyond? What is the ultimate fate of the universe? And how do we, small and fleeting, fit into this vast cosmic tapestry? Black holes are not the end. They are the beginning of understanding, imagination, and the endless quest to know the universe.